Hi, in this video let's look at the important concepts of network fundamentals. In the earlier video, we looked at the raw power of CPU, the speed of the cache, and how memory and SSD work together to handle threats. But here's the reality. Modern high-scale systems don't live on an island. They don't run on one single machine. They run on the hundreds or even thousands of them working in sync. This brings us to the ultimate challenge of distributed systems. How do these machines actually talk to each other? This is the essence of networking. In this video, let us build a proper understanding of machine communication. To understand how that communication works, we first need to define what exactly we are building. At its simplest, a network is just a group of computers connected for the sole purpose of exchanging data. But scale matters. Think of a LAN or a local area network as your home or an office setup. It's private, fast, and contained. When we scale up to the cover cities or countries, we get WAN or wide area network. And what about the internet? That's the final boss. It's like essentially giving a massive global network of networks. Inside a single machine, threads communicate via shared memory, but once we step out of that box, networks become the nervous system that allows these machines to collaborate as one. But for these machines to talk, they first need to find each other. Just like you need a home address to receive mail, every computer on a network needs a unique identity. This brings us to IP addresses and DNS. An IP address is the unique digital address of a machine on a network, something like 142.250.183.14. However, humans aren't great at memorizing strings of numbers. That's why we have DNS, or the domain name system. Think of DNS as the internet's phone book. When you type google.com into the browser, a DNS query happens behind the scenes to convert that name into an IP address. Without DNS, you would have to memorize a random string of numbers for every website you visit. In system design, understanding this lookup is crucial because it's the very first step in every single request. Now that we know where we are going, we need to decide how we want to travel. Do we need a guaranteed safe arrival or do we need to get the data there as fast as possible? When machines communicate, they use protocols to decide how data is packaged and sent. The two heavyweights you need to know about are TCP and UDP. TCP is your reliable option. It ensures data is ordered and checks for errors. If a packet gets lost, TCP makes sure it is sent again. We use this for things that cannot fail, like web requests and database connections. UDP, on the other hand, is built for speed. It sends data without waiting for confirmation. There's no guarantee it arrives, but it's incredibly fast. This is why it's the go to for streaming, gaming, and voice calls, where a tiny bit of lost data is better than a massive lag spike. So, what is the core system design rule here? It's always a reliability versus speed trade off. But how does TCP actually achieve that high level of reliability? It all starts with a formal introduction between two machines. Before a single byte of data can be sent over TCP, a connection must be established through a process called three-way handshake. Think of this as a formal greeting. Step 1, the client sends a synchronous packet, basically saying, "Hey, I want to talk." And step 2 will be like the server replies with a synchronous acknowledgement saying, "I hear you and I'm ready to." In the last step, the client sends a final acknowledgement saying, "Got it, let's start." Only after this three-step dance is finished can the actual data flow. For a system designer, the key takeaway is that this handshake adds extra latency. Every trip back and forth takes time, and this is exactly why networking choices have a direct impact on your system's performance. So we've established the connection, but what does the actual conversation look like? Most of the time, we aren't just sending raw bytes, we are using the standard language of the web. On top of TCP sits HTTP, the application protocol that powers the web. HTTP follows a straightforward request response model. A client like your browser sends a request, and the server then processes that and responds with the data you asked for. But there's a catch. Standard HTTP is sent in plain text, meaning anyone listening on the network can read it. That's where HTTPS comes in. It is simply HTTP wrapped in TLS encryption. This protects everything from passwords and session tokens to payment information. In any modern system you design, there is no debate at all. Always use HTTPS to ensure your users' data stays private. We've talked about how data moves, but in world of high performance systems, we need to measure how well it moves. This brings us to the three important metrics that define the user experience. To optimize any distributed system, you must master three critical metrics: latency, bandwidth, and throughput. First is latency. This is the time delay. It's how long it takes for a single piece of data to travel from point A to point B, and it's usually measured in milliseconds. Next is bandwidth, the maximum capacity of your pipe. Think of a 100 megabits per second connection as a highway with many lanes. Finally, there's throughput. It is the actual amount of data successfully transferred per second. Here is a vital system design insight. High bandwidth does not guarantee low latency. You have a massive 10-lane highway, but if the speed limit is 5 miles per hour, your data is still going to arrive late. Understanding the difference is the key to building systems that actually feel fast. Now, what happens when your system becomes so popular that one single machine can't handle the load anymore? To keep things running smoothly, we need a way to distribute that traffic. What happens when one server hits its limit? In the real world, we don't just upgrade a single machine vertically forever. Instead, we scale horizontally. We add more servers and put a load balancer in front of them. The load balancer acts like a traffic police, distributing incoming requests evenly across the server fleet. This is a game changer for system design because it enables high availability. That is, if one server dies, the other stays up. Fault tolerance. Your system keeps running despite all the failures. Scalability. You can keep adding servers as your user base grows. With the load balancer in place, we are no longer just looking at a network, we are officially entering the world of distributed systems. Until now, we have covered the infrastructure and hardware that makes communication possible. But how do different applications actually format their data to understand each other? In the next video, we move to the top of the stack to explore application layer protocols including REST, gRPC, and WebSockets. I'll see you in the next one. Thank you.